October 29th, 2025, the day astronomers had been waiting for. After years of tracking its inbound journey, the interstellar object known as 3I Atlas finally reached Perihelion, passing just over 0.78 astronomical units from the Sun. It was expected to behave predictably: a steady increase in brightness, a smooth trajectory, and a gradual fade as it continued on its way out of the solar system. Instead, within hours of that closest approach, data from multiple observatories began to diverge from every established model. The European Space Agency's SOHO probe recorded an unexpected drop in visible magnitude during the hours following perihelion, while the Lowell Discovery Telescope in Arizona noted a subtle shift in the angle of the object's tail, a movement inconsistent with the solar wind direction at the time. These weren't dramatic changes, but they were enough to trigger immediate coordination between data centers, including the Minor Planet Center and the Harvard-Smithsonian Center for Astrophysics. In astrophysical terms, such deviations are rare but meaningful. The object's brightness curve showed a short-lived decrease instead of the expected flare-up. That suggested uneven outgassing, surface venting, or even a minor breakup of volatile layers near its nucleus. Nothing indicated anything artificial, but the anomaly was real, measurable, and repeatable across independent telescopes. Over the following days, as 3I Atlas moved past the Sun's glare, tracking stations began piecing together what had actually happened during those critical hours, and the evidence points to a chain of physical reactions that no prediction fully captured. On October 29th, 2025, the interstellar object known as 3I Atlas reached perihelion, its closest approach to the Sun. At that moment, it was travelling at tremendous speed on a hyperbolic path that would eventually carry it back out of the solar system forever. Astronomers had been preparing for this exact event for months, expecting a fairly predictable outcome. Models suggested a gradual increase in brightness as the object neared the Sun, followed by a sharp decline once it passed the point of maximum heating. But when the day finally arrived, the data that came in told a slightly different story. From a technical standpoint, perihelion refers to the precise point in an orbit when an object is closest to the Sun. For 3I Atlas, that distance was about 0.78 astronomical units, roughly 100 to 16 million kilometers. It was far enough to avoid complete disintegration, yet close enough for solar radiation to cause intense stress on its surface. As the object accelerated through this region, its velocity exceeded 40 kilometers per second relative to the Sun, producing a brief but critical observational window. That period, the perihelion window, was when astronomers expected to learn the most about its true nature. The problem was visibility. From Earth's perspective, 3I Atlas was positioned too close to the Sun in the sky to be observed safely by most ground-based telescopes. During that time, it was essentially hidden behind the Sun's glare. The only instruments capable of watching it directly were solar observation spacecraft, such as SOHO and ESA's Solar Orbiter, which used coronagraphs to block the Sun's disk and capture faint objects nearby. Those instruments provided the only reliable data during the hours around perihelion. This limited viewing opportunity meant that every frame, every light curve, and every spectroscopic measurement mattered. Astronomers knew that once the object passed the Sun, it would fade quickly as it moved away, and many subtle changes might never be seen again. They were especially focused on monitoring its brightness curve, the gradual increase and decrease in reflected sunlight that reveals how a comet or interstellar object responds to heat. Before perihelion, the predictions were clear. 3I Atlas was expected to brighten steadily as sunlight heated its volatile compounds, causing outgassing and the development of a stronger tail. After perihelion, those emissions would likely stabilize, and then fade as the object cooled on its way back toward interstellar space. That was the baseline expectation drawn from studying other long-period comets, such as C/2019 Borisov and 2I/Borisov, the first confirmed interstellar visitor of its kind. But the predictions depended on an important assumption, that 3I Atlas behaved like a typical comet. It did not. The first signs of deviation came in the hours after perihelion, when early analysis of brightness measurements indicated an unexpected drop instead of a flare-up. This subtle but measurable change challenged every pre-existing model. It hinted that something during perihelion had interfered with the normal heating process. Perhaps uneven surface activity, a partial collapse of volatile layers, or the exposure of darker, non-reflective material. Another factor complicating the picture was the object's inclination, the steep angle at which it crossed the plane of the solar system. 3I Atlas approached from above the ecliptic on a retrograde path, meaning it moved opposite the direction of the planet's orbits. This geometry not only limited viewing opportunities but also exposed the object to different solar wind angles and radiation pressures than most comets experience. That unique alignment may have affected how dust and gas were released from its surface, altering its overall brightness profile. Thermal modelling later suggested that when the object reached perihelion, its surface likely experienced rapid heating on one hemisphere and extreme cooling on the other. Such temperature contrasts can produce internal stress fractures. In ordinary comets, this sometimes leads to minor fragmentation or outbursts of dust and gas. For an interstellar body like 3I Atlas, one that had likely travelled for millions of years through the frozen darkness of interstellar space, that stress could have caused even more unpredictable behaviour. Astronomers reviewing the post-perihelion data found other curious details. The tail of 3I Atlas, faint but visible in several chronograph images, appeared to shift slightly off alignment with the solar wind direction. That shift suggested that internal jets of gas were pushing the dust unevenly, possibly due to a rotating nucleus releasing material from specific regions rather than uniformly across its surface. This kind of asymmetric jetting had been seen before in comets, but the degree of misalignment in this case stood out. Because of the geometry of the perihelion passage, many of these effects unfolded out of sight of Earth-based observatories. When the object finally reappeared from behind the sun's glare in early November, telescopes began to re-establish tracking and found a slightly dimmer object than expected. That meant whatever had occurred during perihelion had lasting consequences, not catastrophic ones, but measurable and real. In essence, the perihelion window became both an opportunity and a mystery. It was the critical moment when the object's physical behaviour diverged just enough to draw attention, but not enough to suggest disintegration. The solar heat had clearly triggered some form of reaction, perhaps localised outgassing, surface cracking, or exposure of non-volatile material. Yet the object remained intact, continuing on its outbound trajectory through the solar system. This was not a dramatic failure of prediction, but it was a subtle reminder of how limited our understanding of interstellar objects still is. 3I Atlas behaved close to what was expected, but with enough variation to make astronomers question their models. Small differences in brightness, tail geometry, or rotation rate can hold enormous implications for what these bodies are made of and how they evolve under solar stress. By the time the perihelion window closed, 3I Atlas had already begun fading from view. It continued to accelerate outward, passing beyond the sun's gravitational reach on its way back to interstellar space. Yet the questions born from that narrow window remain. Why did its light dip instead of brighten? Why did its tail drift slightly off axis? And did those changes reveal internal weaknesses, or simply a new kind of material behaviour we've never observed before? For now, the answers lie in the data gathered during that short, intense encounter with the sun. The next step is to look closer at what the light curve itself reveals, the drop in brightness that turned this ordinary perihelion into one of the most studied moments in modern interstellar astronomy. In the hours after 3I Atlas passed its closest point to the sun, astronomers began to notice something unusual in its recorded light curve, a sudden and measurable drop in brightness. This wasn't the faint flicker of an instrument error or the effect of solar glare. It was a real decrease, one that appeared in data from multiple observation points. Under normal circumstances, a comet or interstellar object nearing perihelion brightens dramatically as heat from the sun causes ice and gas to sublimate, creating a glowing coma and a long reflective tail. But 3I Atlas defied this expectation. When analysts compared images taken just before and immediately after perihelion, they found that the object's apparent magnitude, a measure of brightness, had dropped instead of increased. The change wasn't enormous, but it was enough to stand out. This dimming persisted for several hours before stabilizing, leading scientists to suspect that something on or within the object had altered the way it reflected sunlight. The first hypothesis was straightforward. Surface material might have collapsed or vented gas unevenly, covering previously reflective ice with darker, dust-rich material. To understand why this matters, it helps to know what a light curve reveals. Each recorded data point represents how much sunlight an object reflects toward Earth or an observing spacecraft. A rising curve indicates increasing surface activity, while a dip can signal either a temporary shadowing effect, rotational change, or physical transformation, such as a fragment breaking off or a surface layer darkening. In this case, the drop came too quickly to be explained by rotation alone. Something physical had changed. The SOHO and Solar Orbiter spacecraft recorded faint but consistent differences between pre- and post-perihelion imagery. At first, researchers thought solar interference might have distorted the readings, but once ground-based observatories regained visibility in early November, their data confirmed that 3I Atlas was, indeed, slightly fainter than predicted. The dimming event had been real. A few possible explanations emerged. One involves outgassing asymmetry, a process in which volatile gases escape from specific regions rather than evenly across the surface. When this happens, material jets outward in narrow plumes, sometimes ejecting dust clouds that momentarily obscure reflected sunlight. Another explanation points to thermal fracturing, when parts of the nucleus crack due to intense temperature shifts. As sunlight heats one side while the opposite side remains frozen, mechanical stress can cause surface crusts to shatter, releasing darker subsurface material. The result, a visible decrease in brightness even as the object remains active. A third possibility centers on the orientation of the tail. Cometary tails are shaped largely by the solar wind and the object's own motion, but if the release of gas and dust occurs unevenly, the tail can shift away from the expected direction. This reorientation might reduce how much reflected light reaches Earth temporarily, depending on the viewing angle. Data taken by coronagraph instruments around perihelion hinted at a small change in tail alignment, a subtle tilt that may have contributed to the apparent brightness drop. At this stage, astronomers exercised caution. They had only limited data from the period when the object was near the Sun, and each measurement carried some uncertainty due to background glare. However, the consistency between different instruments strengthened confidence that the anomaly was genuine. It was not an observational artifact, but a physical effect. The drop in brightness also coincided with another phenomenon, a slight change in spectral composition. Preliminary analysis of reflected sunlight indicated a modest increase in carbon-rich dust and a decrease in volatile signatures like cyanide and diatomic carbon. This suggested that the bright icy layer near the surface may have vaporized more quickly than expected, leaving behind darker, less reflective material. In other words, the object's skin had changed. This transformation is significant because it reveals something about the age and resilience of interstellar matter. Objects like 3I Atlas have spent millions of years in deep space, where their surfaces become coated with complex organic compounds formed by cosmic radiation. When they finally encounter a star, that coating burns away or breaks apart, exposing pristine material beneath. If the surface melted too quickly during perihelion, it could have produced short bursts of gas followed by periods of reduced reflectivity, precisely what the light curve shows. Another line of inquiry considered whether rotation played a part. Photometric readings before perihelion indicated that 3I Atlas rotated slowly, with a period possibly exceeding 10 hours. If the Sun heated one hemisphere more than the other, volatile jets could have acted like miniature thrusters, altering the spin. A small increase in rotation rate could redistribute the direction of gas release, affecting brightness temporarily. Later chapters will show that minor spin changes did in fact occur, but the timing of the light curve drop aligns too precisely with perihelion to be fully explained by rotation alone. The scientific community quickly began comparing this event to past observations of 2I/Borisov, another interstellar comet that showed mild fragmentation near perihelion in 2019. The difference was scale. While Borisov's breakup was visible and obvious, 3I Atlas displayed no such violent disintegration. Its brightness drop was modest, its nucleus remained intact, and its trajectory continued smoothly outward. That made the anomaly even more intriguing, small enough to avoid catastrophe, but large enough to challenge theoretical models. By early November, as 3I Atlas re-emerged from the solar glare, telescopes resumed regular observation. It appeared stable, still emitting a faint tail but maintaining a lower brightness than expected. This confirmed that the light curve drop wasn't just a temporary shadow or optical effect. The event had altered the object's reflectivity in a lasting way. Researchers at various observatories compiled their findings and reached a cautious consensus. 3, E Atlas had likely experienced a localized surface event during perihelion, a venting or collapse that released dust and changed the scattering properties of its coma. The physics behind it remain under study, but the consequences are clear. Even minor irregularities at perihelion can tell us how interstellar bodies react under solar heating and reveal details about their structure that would otherwise remain hidden. The brightness anomaly, then, wasn't merely an observational curiosity. It became the first concrete sign that perihelion for 3I Atlas hadn't gone entirely as predicted. It was a clue, one that led astronomers to re-examine everything that followed: the shifting tail, the potential surface cracking, and the post-perihelion trajectory. The drop in light wasn't a random fluctuation, it was a signature, a faint pulse of information sent from an object older than the solar system itself, responding to its first encounter with another star in perhaps billions of years. As 3I Atlas moved beyond the sun's glare in early November, its faint but distinct tail began to reappear in new telescope imagery. What scientists expected to see was a straightforward configuration: a main dust tail pointing directly away from the sun under the influence of solar radiation pressure, and possibly a faint ion tail shaped by the solar wind. Instead, the first post-perihelion images revealed something more complicated. The tails were misaligned, slightly off the expected axis, tilted in a way that couldn't be explained by the solar wind alone. Normally, this kind of behavior would be attributed to observational angle or incomplete data, but multiple observatories, each using different instruments and vantage points, confirmed the same pattern. The dust tail appeared to bend at a sharper angle, suggesting that dust particles weren't being ejected evenly. Meanwhile, the ion tail, which should trace the flow of charged particles along the interplanetary magnetic field, appeared thinner and less distinct than expected. For astronomers studying the geometry of cometary tails, this mismatch immediately stood out. To understand the significance, it helps to recall how a tail forms. When sunlight heats an object like 3I Atlas, volatile ices sublimate and release jets of gas that drag dust particles into space. The sun's radiation pressure then pushes these particles outward, creating a broad, curved tail that always points away from the sun. The orientation of that tail, its angle relative to the object's path, is highly predictable. If it's not aligned, something internal is driving it off axis. In this case, the likely culprit was asymmetric outgassing. Instead of venting material evenly across its surface, 3I Atlas seemed to release gas from a few concentrated regions. Those jets acted like miniature thrusters, altering both the direction of expelled dust and the apparent position of the tail. Thermal models based on the object's size and estimated rotation period supported this theory. If one side of the nucleus remained hotter for longer, it would emit more gas and dust, producing precisely the kind of misalignment observed. There was another subtler effect at play: rotation. After perihelion, astronomers began to detect small variations in the object's light curve that hinted at a change in spin. This was consistent with the idea that uneven outgassing could have accelerated the nucleus, shifting its rotational axis. A shift of even a few degrees could alter how sunlight reached different surface regions, reinforcing the asymmetric ejection pattern. The result would be a constantly evolving tail, twisting and bending over days rather than pointing steadily outward. By comparing sequential images taken over several nights, analysts noticed that the tail's angle changed slightly from frame to frame. This wasn't due to movement across the sky, it reflected real structural change. Dust models simulated under these conditions showed that fine particles could have been ejected at low velocities from one dominant jet, producing a curved tail that lagged behind the nucleus before catching the solar wind's push. The visual effect matched the observations perfectly: a misaligned, almost folded tail that gradually straightened as the days went on. For context, similar misalignments had been documented in other comets before, particularly those with irregular shapes or non-uniform surfaces. What made 3I Atlas unusual was that it displayed this feature immediately after perihelion, when one would expect outgassing to be strongest and most uniform. That timing suggested something more specific had occurred during the Sun encounter. Perhaps a surface fracture had opened a new vent, or an older one had collapsed, redirecting the flow of material. The spectroscopic readings taken during this period backed up that idea. There was a slight increase in neutral sodium emissions, which often appear when dust grains are freshly exposed or heated. At the same time, gas emissions decreased, implying that the volatile material was being released more sporadically. Together, these patterns painted a picture of a surface undergoing localized restructuring, a process that could shift the outflow of dust and tilt the tail's axis. Another possible explanation lies in the solar wind environment at the time. Late October and early November saw moderate geomagnetic activity from a coronal mass ejection that propagated through the inner solar system. The variable magnetic field could have influenced the ion component of the tail, causing it to twist relative to the dust component. In composite imagery, this would make the two tails appear disconnected or bent. While this effect alone wouldn't cause the degree of misalignment observed, it could have contributed to the overall distortion. For mission planners and theoretical modelers, the implications of the misalignment were important. It meant that 3I Atlas was not a simple, uniform body reacting passively to sunlight. It was a complex rotating structure responding dynamically to its environment. Each change in temperature or spin produced measurable effects on its appearance. Even without catastrophic fragmentation, the object was evolving in real time, teaching astronomers how interstellar material behaves when subjected to the sun's influence. In the weeks that followed, the tail's position angle began to stabilize. Observations from both hemispheres showed that the misalignment gradually diminished as the object moved farther from the sun and its activity level decreased. This confirmed that the phenomenon was transient, a temporary imbalance in gas flow rather than a lasting structural deformation. But the event left a permanent mark on the data record, adding one more anomaly to a growing list that proved Perihelion had not gone exactly as the models predicted. For scientists, the misaligned tail was more than a curiosity. It was evidence that even small thermal or rotational shifts can produce visible, large-scale effects in space. It demonstrated that interstellar visitors are not inert relics from other star systems. They are active, unpredictable bodies that challenge assumptions about how comets behave under stress. By the second week of November 2025, new high-resolution images of 3I Atlas were arriving daily. What astronomers noticed first was not its brightness or tail, but the faint texture surrounding its nucleus, a subtle haze that hadn't been present before perihelion. It wasn't large enough to suggest a breakup, but it was too consistent to dismiss as instrument noise. The data hinted that 3I Atlas might have shed small pieces of surface material as it rounded the sun. Fragmentation is a well-known stage in the evolution of icy bodies. When a comet's nucleus warms unevenly, volatile pockets expand under the surface until they rupture, throwing off chunks of rock, dust, or ice. In most cases, these fragments disperse quickly and fade. But for interstellar visitors like 3I Atlas, bodies that have likely remained frozen for millions of years, even minor stress can expose interior layers that have never seen sunlight before. That's why this faint diffuse glow drew so much attention. The early indications came from stacked image analyses. Several teams used time series exposures to compare the object's central brightness profile. Instead of a smooth, symmetric light distribution, the core appeared slightly extended, almost as if a cloud of fine dust surrounded it. When motion tracking algorithms were applied, small bright specks moved outward along the same vector as the primary tail but at slightly different velocities. None of them were large enough to qualify as distinct fragments, yet together they suggested that the surface was venting material in short bursts. Thermal modelling provided a plausible mechanism. At perihelion, surface temperatures on the sun-facing side of 3I Atlas may have exceeded 200 degrees Celsius. The shaded side, still coated in primordial ice, would have remained near -100. That level of differential heating can generate internal cracks and force pockets of gas to escape violently. Each minor outburst can lift fragments only a few meters across, barely detectable at astronomical distances, but enough to produce the dusty veil seen in post-perihelion imagery. Spectroscopic readings reinforced this picture. Observers detected a transient increase in the presence of sodium and magnesium lines, elements typically released when new surface material is exposed. These emissions faded within days, implying that whatever event had occurred was brief and localized. No evidence pointed to a full structural failure or nuclear split. Instead, scientists described it as a micro-fragmentation episode, similar in scale to what has been observed in some Jupiter family comets after perihelion. Even small surface disruptions can have measurable effects on the dynamics of an object travelling through space. The release of material changes its mass distribution and can act as a subtle form of thrust. In most cases, this acceleration is negligible, but when the object is moving at interstellar velocity, over 40 kilometers per second, even a tiny impulse can produce noticeable deviations over time. This realization led researchers to watch 3I Atlas's trajectory even more closely, comparing each new positional measurement to the orbital models generated before Perihelion. Interestingly, the object's light curve showed faint periodic flickers superimposed on its gradual fading. These fluctuations corresponded with possible rotational modulation, meaning that as the nucleus turned, certain regions reflected sunlight differently, or jets became active only when illuminated. If parts of the surface had fractured or collapsed, they could have altered the object's spin, slightly changing its rotational period. A similar phenomenon was documented with Comet 67P/Churyumov-Gerasimenko during the Rosetta mission, when a symmetric outgassing slowly modified the rotation rate. What made the case of 3I Atlas scientifically valuable was that the changes were measurable, but moderate. It hadn't disintegrated like some short-period comets do when approaching the Sun. Rather, it appeared to have endured perihelion mostly intact, suffering only superficial losses. This endurance gave astronomers a rare chance to study how an interstellar nucleus responds to solar heating without catastrophic consequences. It was the cosmic equivalent of a stress test, a small-scale failure that revealed the structure's underlying resilience. Data collected from November 8th to 15th showed a gradual stabilization of the object's brightness. The diffuse haze diminished, and the nucleus regained a cleaner, more defined profile. This pattern suggested that the micro-fragmentation phase was temporary. Dust released during the event dispersed along the tail, becoming part of the broader debris stream. The lack of recurring activity in later images confirmed that the structural response had run its course. For researchers, this episode underscored the importance of continuous monitoring. Without near real-time observations from multiple facilities, such subtle events could easily go unnoticed. It also provided a cautionary insight into future missions designed to intercept or study interstellar objects. Even modest heating can trigger rapid and unpredictable outgassing, potentially endangering spacecraft if approached too closely. By mid-November, the conclusion was clear. 3I Atlas had indeed experienced a brief period of surface instability as it passed perihelion. The event released a small cloud of dust and possibly tiny fragments, enough to alter the light curve and tail appearance, but not enough to change the object's fundamental structure. It remained a single, coherent body, battered but intact, continuing its journey outward into the dark. Yet one lingering question remained. Did that fragmentation, however minor, impart any measurable push on its orbit? If so, its predicted trajectory might already be diverging from the initial models. Astronomers began recalculating its path using the newest data, looking for any sign that the object's outbound course had shifted even slightly. By the middle of November 2025, 3I Atlas had moved far enough from the Sun to allow precise astrometric tracking again. Telescopes in both hemispheres, ranging from small university observatories to larger instruments like the Subaru telescope in Hawaii, began gathering fresh positional data. Each new observation was compared to pre-perihelion trajectory predictions generated by the Minor Planet Center and various orbital modeling programs. What emerged from these comparisons was subtle but intriguing. 3I Atlas was still on course, but not perfectly. Before perihelion, its trajectory had been modelled as a hyperbolic escape path with an eccentricity slightly above 1, confirming it was unbound to the Sun and would eventually leave the solar system entirely. Its motion followed the classical gravitational pattern expected from a natural interstellar object influenced only by solar gravity and radiation pressure. But after perihelion, when enough new measurements were collected to recalculate its ephemeris, analysts found minute residuals, small discrepancies between predicted and observed positions. These deviations were tiny, within the range of a few arcseconds, yet consistent across multiple observatories. That consistency made them significant. If the errors had been random, they could be blamed on atmospheric distortion, instrument calibration, or measurement noise. But because they followed a coherent pattern, scientists suspected a real physical cause, non-gravitational acceleration. Such acceleration can result from asymmetric outgassing, when a comet or similar body vents material unevenly, producing a small but continuous thrust. Over time, this thrust slightly alters the object's velocity and trajectory. To test the idea, orbital dynamicists reintroduced outgassing parameters into their models. When they included a weak, sunward-directed acceleration consistent with low-level jet activity, the residuals nearly disappeared. The adjustment required was small, equivalent to a thrust force of only a few 10,000ths of a newton, but at interstellar speeds, even that was enough to account for the observed deviation. This result supported what earlier chapters suggested, that 3I Atlas's perihelion passage involved active surface changes releasing gas unevenly. These findings place 3I Atlas in a familiar scientific context. The same kind of non-gravitational motion had been observed in previous interstellar visitors, notably 1I/Oumuamua in 2017 and 2I/Borisov in 2019. In both cases, small deviations from pure gravitational motion sparked debates about whether the cause was outgassing, radiation pressure, or something else entirely. With 3I Atlas, however, the explanation was more straightforward because telescopic data actually showed residual gas and dust activity. There was no need for exotic assumptions. The object was behaving as a natural comet should, just not exactly as predicted in magnitude or timing. Still, the nature of the deviation carried lessons. Calculations showed that the post-perihelion acceleration vector wasn't purely away from the Sun, as one would expect if sublimation were uniform. Instead, it had a slight tilt relative to the Sun object line, suggesting the strongest jets may have been located on the hemisphere that faced the Sun obliquely. This directional bias could also explain the earlier tail misalignment. Both phenomena pointed to uneven activity concentrated on one side of the nucleus. As data accumulated, analysts built a refined trajectory model that incorporated these forces. The new model predicted that 3I Atlas would pass beyond the orbit of Mars by late January 2026 and cross Jupiter's orbital distance by the end of the following year. By that point, its brightness would have dropped below detection limits for most amateur telescopes, leaving only major observatories capable of tracking it. The object would then continue toward interstellar space on a slightly altered but still hyperbolic path. What mattered most was that the deviation remained consistent with natural causes. No sudden directional jumps, no erratic accelerations, just a steady, weak push that matched the scale of gas release measured spectroscopically. This provided one of the clearest demonstrations yet that interstellar comets behave much like solar system comets, despite their alien origin. It also reinforced that the surface activity of such bodies can meaningfully influence their escape trajectories even long after perihelion. During post-analysis, teams from the European Space Agency and several research institutes ran forward simulations projecting the object's position decades into the future. Assuming the outgassing gradually ceased as it cooled, 3I Atlas would leave the solar system at roughly 42 kilometers per second relative to the Sun, heading toward the constellation of Centaurus. No gravitational encounters with the planets were expected. In simple terms, its journey through our neighbourhood was already ending. The process of checking the trajectory also revealed how sensitive our instruments and models have become. Just 2 decades earlier, such fine-scale variations would have been impossible to detect for an object this faint and distant. Now, with coordinated observations and improved astrometric precision, researchers can measure a deviation of mere tens of meters per second in an object hundreds of millions of kilometers away. This level of detail transforms interstellar astronomy from a field of discovery into one of precise diagnostics. We are not just finding these objects, but beginning to understand their mechanics. The trajectory analysis closed one chapter of uncertainty but opened another. The path was stable, but the forces that slightly altered it hinted at complex interactions between rotation, outgassing, and internal structure. Each parameter, how fast it spins, where the jets are located, how surface fractures develop, shapes its movement through space. Understanding that interplay will be key to interpreting future interstellar visitors. By late November, the consensus among observatories was clear. 3I Atlas remained on an outbound course consistent with natural dynamics, slightly adjusted by non-gravitational forces during perihelion. Its orbit confirmed its interstellar origin beyond doubt, and demonstrated once again that these visitors, though rare, follow the same fundamental physics as everything else in the cosmos. By late November 2025, the brightness of 3I Atlas had stabilized enough for astronomers to begin collecting consistent spectral data once again. This stage of observation was crucial because spectra reveal far more than light curves or photographs can. They expose the object's chemical fingerprint, the unique combination of elements and molecules reflecting or emitting light at specific wavelengths. And when compared before and after perihelion, those fingerprints can tell us exactly how the Sun altered the object's surface and composition. The initial post-perihelion spectra were obtained using medium-resolution instruments on several major observatories, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii. These data were complemented by smaller but high-cadence observations from amateur networks equipped with low-dispersion spectrographs. What the teams found confirmed what many had suspected since the brightness drop. The surface chemistry of 3I Atlas had changed. Before perihelion, the object's spectrum showed the familiar signatures of a volatile rich body. There were clear bands associated with cyanogen, Cn, diatomic carbon, C2, and traces of hydroxyl, OH, all common products of ice sublimation in comets. But after perihelion, those lines were weaker, while new features emerged, particularly a stronger continuum in the red and near-infrared wavelengths. That shift indicated an increase in dust scattering and the exposure of darker, more carbonized material. In simpler terms, the icy layer that once covered the surface appeared to have been stripped away, leaving behind a crust of non-volatile residue. This transformation wasn't unique to 3I Atlas, but the rate and degree of change were surprising. Most comets that pass this close to the Sun lose volatiles gradually. 3I Atlas, however, seemed to have undergone a rapid chemical transition during its perihelion passage, as if the heating reached deeper layers faster than expected. Models of thermal conductivity support this possibility. If the object's outer crust was fractured by stress, sunlight could have penetrated below the surface, triggering explosive sublimation in confined pockets. The gas released in those bursts would carry away reflective ice and leave darker compounds behind. Precisely the spectral pattern that was now visible. In the weeks following perihelion, the Cn and C2 emissions did not recover, even as the object moved into cooler space. This suggested that the volatile inventory near the surface had been permanently depleted. At the same time, the broadband spectrum flattened, indicating that fine-grained dust was still present, but now dominated by silicate and carbon-rich particles. Astronomers described it as a thermal skin effect, a shallow but irreversible layer of processed material covering the nucleus, similar to what has been seen on long-period comets that have survived multiple close solar passes. One particularly interesting finding came from polarization measurements. Polarized light analysis helps determine the texture and size of dust grains. Observations of 3I Atlas showed an increase in polarization degree compared to its inbound phase, implying that the post-perihelion dust particles were larger and rougher. Smaller icy grains had either melted or been blown away, leaving behind heavier, more irregular fragments. This change supported the hypothesis that perihelion heating stripped the surface of its lighter components. Meanwhile, infrared spectra revealed weak but distinct absorption bands near 3.4 microns, typical of complex organics, sometimes referred to as tholins. These compounds form when simpler carbon-bearing molecules are irradiated over long timescales in space, suggesting that parts of 3I Atlas's interior were ancient and had remained untouched since before it entered our solar system. The presence of these organics deepened scientific interest. It meant the object carried chemical information from another star system, possibly one with conditions similar to our own early solar nebula. Even as excitement grew, researchers emphasized that all of this still pointed to natural cometary behavior. The disappearance of volatiles, the reddening of the spectrum and the dust composition changes were all consistent with what happens when frozen material encounters the intense energy of the Sun. The difference was that 3I Atlas was not a local comet returning after many cycles. It was an interstellar visitor experiencing solar heating for the first and likely last time. Every reaction was amplified, every effect more dramatic. The data also revealed something subtle but significant. A minor shift in the rotational light signature corresponding to changes in the distribution of reflective material across the surface. This confirmed that the perihelion event had altered not just the chemistry, but also the optical texture of the nucleus. Some regions became darker, others slightly brighter, depending on where new material was exposed. Such variations explain why the object's overall brightness stabilized at a slightly lower level after perihelion. It wasn't fading because it was dying, it had simply changed its face. To put these findings in perspective, scientists compared 3I Atlas's spectral evolution to that of 2I/Borisov, the only other interstellar comet with well-documented spectral data. Borisov's chemistry remained relatively stable during its perihelion in 2019, dominated by carbon monoxide and cyanogen. 3I Atlas, by contrast, showed stronger evidence of thermal alteration and surface processing. This difference may stem from its composition or its trajectory. Borisov passed closer to the Sun, but its nucleus was likely larger and better able to retain ices. 3I Atlas, smaller and possibly more porous, responded more violently to solar heating. By the end of November, most observatories agreed on a consistent conclusion. 3I Atlas had lost much of its accessible volatile material, leaving behind a dark, chemically evolved shell. Its spectral signature had shifted from icy to dusty, from reflective to carbonized. Yet despite those changes, it remained structurally intact, a rare and valuable survivor of an interstellar journey through a stellar furnace. For planetary scientists, these results provided a unique window into the building blocks of other star systems. The ratios of carbon, oxygen, and organic molecules hinted at a composition not unlike that of early solar system comets. That parallel suggested that the processes that form small icy bodies might be universal, repeating across galaxies, producing similar materials wherever stars are born. As December approached and 3I Atlas continued moving outward, the focus of observation began to shift once again, from composition to motion, from chemistry to physics. Astronomers wanted to know whether the thermal and structural changes observed during perihelion had affected the object's spin or stability. Subtle fluctuations in its brightness hinted that the nucleus might be rotating differently than before. As the new spectral data continued to come in, another anomaly began to attract attention. Subtle, rhythmic variations in brightness that hinted at a change in rotation. Astronomers are now closely monitoring 3I Atlas's spin behavior, and early measurements suggest that the object may be rotating differently than it did before perihelion. During its inbound phase, photometric readings taken throughout September and early October 2025 indicated a slow, stable rotation, possibly once every 10 to 12 hours. That pattern was regular enough to help predict how sunlight would fall across the object's surface as it approached the Sun. But after perihelion, the pattern began to shift. The same photometric datasets that once produced a steady periodic light curve now show irregular peaks, suggesting either a change in rotation rate or a reorientation of the nucleus. Observers are currently comparing pre- and post-perihelion light curves frame by frame. The variations appear too systematic to be caused by dust interference or instrument noise. Instead, they likely point to real torques generated by asymmetric outgassing. When one side of the nucleus vents more gas than the other, the resulting thrust acts like a miniature rocket engine, imparting small but continuous rotational acceleration. This is a well-documented effect in active comets, and it seems to be happening again here. Teams analysing these shifts estimate that the spin period could now be shorter, perhaps by a few minutes, though the margin of error remains large. Even such a tiny change is scientifically meaningful, because it shows that the perihelion encounter did not only affect the surface and composition of 3I Atlas, but also its internal dynamics. If the object's structure is irregular, like a lopsided potato rather than a sphere, uneven heating can magnify those torques dramatically. Over time, this process could reshape the object's entire spin axis. Infrared data collected this week adds another layer to the picture. It shows temperature fluctuations that appear to move around the surface rather than staying fixed to one region, consistent with a nucleus that is now rotating faster. This rotation may also be altering how gas and dust are released. Observers report short bursts of brightness lasting less than an hour, possibly micro-outbursts triggered when fresh patches of ice rotate into sunlight. The implications go beyond a simple spin-up. If the object's rotation continues to accelerate, internal stress could build up, leading to cracks or even partial fragmentation later on. For now, there is no evidence of structural instability, but the current monitoring campaign aims to catch any sign of changes early. High-cadence imaging from multiple observatories across the globe is being coordinated to track every fluctuation. Each photometric cycle, each spike or dip in light, could reveal new details about how 3I Atlas is reacting to the energy it absorbed during perihelion. What makes this particularly fascinating to researchers is that it's happening in real time. Unlike previous comets that have been observed after their closest approach, this time scientists are following the evolution hour by hour. The data is still raw and incomplete, but it paints a picture of an object in transition, cooling, stabilizing, but still alive with motion. There is also a broader question forming among dynamicists. How typical is this behavior for interstellar visitors? If 3I Atlas is indeed spinning up due to outgassing, it would strengthen the argument that most interstellar objects behave like active comets, responding predictably to solar heating. But if the changes continue or intensify in unexpected ways, it could mean that the internal structure of these bodies is more fragile or heterogeneous than previously thought. For now, astronomers are keeping a close watch. Every rotation, every subtle flicker is being recorded and analysed. The spin behaviour of 3I Atlas has become a window into its internal balance, a delicate dance between sunlight, gas release, and inertia that determines whether it stabilises or unravels as it leaves the inner solar system. As November 2025 advances, telescopes around the world are continuing to image 3I Atlas as it moves steadily away from the Sun. In the newest composite exposures, astronomers are beginning to see a faint elongated structure trailing behind the nucleus, a debris trail that's much thinner than a classic comet tail but persistent enough to confirm active dust release. At first glance, the debris trail might look like just another extension of the main dust tail, but it behaves differently. While the tail responds almost instantly to solar radiation pressure and solar wind, the debris trail moves more slowly, composed of heavier particles that were ejected earlier and are now following slightly different orbital paths. These particles don't scatter sunlight as efficiently as gas or fine dust, which is why the structure appears dim and narrow. But it's there, and it's growing longer every night. Ground-based observatories in Chile and the Canary Islands are now coordinating nightly observations to map this trail. Early modelling suggests that most of the material was likely released during or shortly after perihelion, coinciding with the period when 3I Atlas's surface underwent visible stress and outgassing asymmetry. The trail's alignment matches that timeline perfectly, indicating that small fragments or clumps of dust left the nucleus at low velocity and are now slowly dispersing along its orbital path. This kind of debris field is not uncommon. Many long-period comets leave a trail of heavy dust that can persist for months, sometimes even forming meteor streams when intersecting Earth's orbit centuries later. In the case of 3I Atlas, however, this material will never return. Its trajectory ensures that it will drift outward indefinitely, a silent trace of its brief interaction with the Sun. The debris trail's composition is currently being analysed using reflected light spectroscopy. The readings show a subdued reflectance spectrum dominated by dark, carbon-rich material, suggesting that the particles are similar in makeup to what was found on the nucleus itself. Processed, non-volatile dust left behind after solar heating removed the lighter compounds. There's almost no sign of frozen volatiles in this trail, confirming that what remains is inert material rather than active, sublimating fragments. Photometric studies indicate that the largest grains may be a few millimeters across, far larger than the typical micron-sized dust that forms the glowing tail. That difference is important. It means the debris trail is composed of material ejected slowly, probably during gentle surface shedding rather than explosive outbursts. This supports the idea that 3I Atlas didn't fragment violently, but instead released surface layers gradually as it heated and cooled. Astronomers tracking the trail's evolution are noting how it bends gently under solar gravity. Its curvature offers clues about the timing of the ejection. The earliest portion, closest to the nucleus, is still relatively dense, while the outer regions already begin to thin. Based on its spread, the trail appears to have begun forming just hours after perihelion, exactly when telescopic data first recorded the dip in brightness and hints of surface venting. There's a quiet satisfaction among researchers right now. The debris trail ties together nearly every anomaly observed so far. The brightness drop, the tail misalignment, and the micro-fragmentation signs. Each of those events left behind part of this faint signature in space. Together they confirm that 3I Atlas was never inert during its closest solar approach. It reacted, shed material, and is now carrying the evidence of that reaction out into the void. While the dust is faint and scattered, it remains scientifically valuable, As the trail expands, it provides astronomers with a rare laboratory for studying the particle dynamics of interstellar material, how foreign dust responds to sunlight, solar radiation, and magnetic fields within our system. Observing how this debris diffuses could even refine models of how similar particles behave when ejected from other star systems. In the coming days, the focus of observation is shifting toward long-exposure imaging designed to capture the outermost edges of the trail before it becomes too faint to detect. Researchers are also monitoring whether new dust continues to emerge from the nucleus. So far, no fresh outbursts have been seen, but the gradual fading of the debris field suggests the object is finally stabilizing. The story of the debris trail is one of gradual release, a cosmic breadcrumb path marking where 3I Atlas briefly interacted with our star. Within a few weeks, the dust will disperse beyond detectability, its particles following parallel paths into the dark beyond the planets. As astronomers prepare their next observation windows, one question is beginning to dominate their discussions. What exactly caused this uneven ejection pattern? Was it simply random surface venting, or does it point to deeper structural or compositional layers that only reveal themselves under solar heat? The next chapter delves into that mystery, examining what the outgassing pattern reveals about the interior of 3I Atlas, and what it might tell us about the origins of interstellar matter itself. As new data continues to arrive from observatories tracking 3I Atlas, astronomers are now focusing on the outgassing pattern, the way the object releases gas and dust into space. Understanding this pattern is crucial because it explains nearly every anomaly observed since Perihelion: the brightness drop, the tail misalignment, and even the shift in spin. At this moment, telescopes equipped with high-dispersion spectrographs are monitoring faint emissions near the object's coma, the thin, diffuse envelope of gas surrounding its nucleus. The signals are weak but measurable, and they show that the release of gas is not uniform. Some regions on the nucleus appear almost dormant, while others remain active, emitting jets that pulse as the object rotates. This asymmetric venting suggests that 3I Atlas's surface is a patchwork of volatile and non-volatile zones, a common trait among comets but amplified here by its rapid transition from deep cold to intense solar heat. These uneven jets act as miniature engines. Each time one erupts, it propels the nucleus in the opposite direction by a tiny fraction of a meter per second. Over hours and days, these impulses accumulate, producing the slight non-gravitational acceleration that earlier trajectory checks confirmed. But they also shape the dust environment around the object. Instead of a single, smooth coma, 3I Atlas now displays faint filament-like structures, wisps of material tracing the geometry of the jets as they sweep through space with each rotation. Researchers observing from Chile and Spain report that these filaments appear and fade rhythmically, roughly in step with the estimated spin period. That means the activity isn't random, it's tied to specific regions coming into sunlight. When a jetting area rotates into view, solar heating spikes, the trapped gases expand, and the surface vents violently for a few minutes before cooling again. This pulsing rhythm has become one of the most fascinating aspects of 3I Atlas's post-perihelion behaviour, a kind of heartbeat still echoing from its close pass around the Sun. Spectral analysis of the gas being released reveals that most of it is water vapour, along with traces of carbon monoxide and carbon dioxide. These molecules are typical of cometary ices, but the proportions are unusual. The CO to CO2 ratio appears higher than what's seen in most solar system comets. That suggests 3I Atlas formed in a much colder environment, likely farther from its original parent star, where carbon-bearing volatiles could accumulate more easily. In other words, its chemistry points to a birthplace in a region of deep interstellar frost. At the same time, ultraviolet observations show decreasing emission strength, meaning the overall level of gas production is now falling as the object moves farther from the Sun. The outgassing pattern, while still asymmetric, is slowing down, a sign that the surface is sealing itself under a layer of refractory dust. This is a natural process. As volatile material evaporates, it leaves behind heavier residues that eventually insulate the interior. Once that crust forms, activity drops sharply. However, even as the jets weaken, the lingering asymmetry continues to affect the object's motion and appearance. High-contrast imagery taken this week shows one side of the coma slightly brighter, consistent with dust being ejected preferentially from one hemisphere. This may explain why the tail still appears offset. The uneven flow of material exerts a steady torque, subtly influencing both rotation and trajectory in real time. Dynamic models being developed now simulate this process using small-scale venting zones. When the parameters are adjusted to match the observed outgassing rate, around 1 kilogram of gas per second during the active phase, the resulting virtual object reproduces almost exactly the tail curvature and brightness variations seen in real images. The match reinforces that outgassing, not impact or fragmentation, remains the dominant driver of 3I Atlas's strange behaviour. For planetary scientists, this stage is particularly valuable. It's rare to witness an interstellar visitor adjusting to solar heating in such detail. The outgassing pattern effectively reveals the internal layout of the nucleus, its pockets of ice, fractures, and trapped gases. Each vent corresponds to a fault line or a region where ancient material is being exposed to sunlight for the first time in possibly millions of years. Right now, researchers are racing to gather as much data as possible before the object fades beyond reach. As 3I Atlas moves outward, its activity will decline sharply, and the faint spectral lines used to measure gas composition will vanish into the background noise. The next few weeks may be the last opportunity to capture direct evidence of how an interstellar body behaves after its closest solar encounter. Even in its waning activity, though, 3I Atlas continues to surprise. The fact that it still emits measurable gas despite having passed perihelion more than a week ago means its internal heat is lingering, a sign of deeper thermal conduction than expected. That could imply a denser or more compact nucleus than previously thought, challenging assumptions that such objects are fragile. Each observation made now contributes to a growing picture. 3I Atlas is not a passive chunk of frozen rock, but a dynamic traveller undergoing transformation as it leaves our system. Its asymmetric outgassing acts as a record of its inner structure, a natural code slowly being written across the sky in vapour and dust. As mid-November 2025 unfolds, astronomers are preparing for a brief but critical pause in their ability to observe 3I Atlas. This period, known as the observation gap, happens whenever an object's position in the sky moves too close to the sun's glare, making safe optical tracking impossible. It's a normal part of celestial observation, but for something as rare as an interstellar visitor, even a few days of lost visibility can feel like an eternity. Right now, 3I Atlas is drifting into the twilight zone of our view, too low on the horizon for most ground-based telescopes to follow, yet not bright enough for daytime detection. Observatories in both hemispheres are squeezing in final exposures before it slips beyond the sun's reach. Data collected during this last window show a steady decline in brightness, consistent with cooling and decreasing gas production. The coma is now smaller and less defined, and the once distinct tail appears fainter, nearly blending into background starlight. This momentary disappearance is both expected and frustrating. Scientists know that once the object passes a certain elongation angle from the sun, even the most sensitive instruments can no longer isolate its faint signal. Space-based assets like the Solar and Heliospheric Observatory, SOHO and Solar Orbiter may still capture limited imagery, but for most researchers the next week or two will be a waiting period, a time to analyse the data already gathered and prepare for its re-emergence. During this observation gap, astronomers are focusing on consolidating everything learned so far. Light curves, spectral readings, and trajectory measurements are being cross-checked and remodelled to refine estimates of the object's spin rate, mass loss, and gas production. Teams are comparing data from multiple observatories to ensure that every anomaly, from the early brightness drop to the asymmetric jets, is understood within the same physical framework. Even without new images, there's plenty to study. For example, scientists are now re-evaluating the thermal conduction inside the nucleus. The fact that 3I Atlas remained active for days after perihelion suggests that heat is still travelling inward, sublimating ices deep beneath the crust. Models indicate that this residual heat could sustain low-level outgassing well into December, even while the object remains invisible from Earth. If that's the case, by the time it becomes observable again, its coma may look very different. Smaller, colder, but still alive. The observation gap also highlights just how much collaboration modern astronomy depends on. Data from professional observatories, space agencies, and independent astronomers are being pooled into shared databases so that analysis continues even when direct observation stops. The collective effort ensures that no piece of information is lost, and it allows scientists to continue tracking the object's expected position even while it hides behind sunlight. Right now, the focus has shifted toward predictive modelling. Researchers are running simulations to determine what 3I Atlas will look like when it re-emerges on the opposite side of the Sun in early December. These models account for dust expansion, outgassing decay, and the slight non-gravitational acceleration detected earlier. The goal is to know exactly where and how to find it again once the glare subsides. There's also a sense of quiet anticipation. Every interstellar visitor teaches something new, and 3I Atlas has already rewritten expectations about how these objects behave near stars. The temporary loss of visibility gives scientists time to process the magnitude of what they've seen. A real-time transformation of an alien body under solar heat. For now, observers describe the feeling as paradoxical. The object that has consumed weeks of non-stop attention is still out there, moving silently through space, yet unseen. They can calculate where it is to within a fraction of a degree, but they can't look at it directly. The only evidence of its continued existence is a set of numbers, coordinates, brightness estimates, and trajectory plots scrolling across monitors in dark observatories around the world. The gap will last only a short time, but when 3I Atlas reappears, astronomers expect a slightly different object. Dimmer, quieter, but perhaps more stable than before. The hope is that its outbound leg will confirm what the inbound phase suggested, that even interstellar ice can survive a solar encounter without total destruction. As December approaches and the observation gap nears its end, telescopes will once again turn toward the eastern dawn sky, ready to reacquire their target. And when they do, they'll not just be watching for its return, they'll be looking for signs of recovery, hints that the object has settled into a new equilibrium after its brief and violent encounter with our Sun. It's now early December 2025, and the long-awaited moment is beginning. After weeks hidden in the Sun's glare, 3I Atlas is slowly reappearing in the pre-dawn sky. For astronomers, this marks the end of the observation gap, and the start of the trajectory recovery phase, when fresh measurements will determine whether the object has remained on course or shifted subtly under the forces of its own activity. Observatories across the globe are now scanning the region of the sky where predictive models placed it. The search began quietly, with wide-field exposures taken from the southern hemisphere, then gradually expanded as new detections came in. By December 4th, the first faint signal matched expectations almost perfectly. A diffuse object, magnitude around 15, right where the model said it would be. Within hours, confirmation came from additional observatories. 3I Atlas had been found again. The relief among researchers is palpable. Losing sight of an interstellar body always carries risk. If calculations are off by even a small fraction, reacquiring it can take days or weeks. But the new data show that the orbital predictions held up with impressive accuracy. The slight non-gravitational acceleration identified in November, caused by uneven gas release, had been correctly factored into the models. The trajectory recovery confirms that 3I Atlas remains on its projected hyperbolic escape path, continuing outward from the Sun at about 42 km per second. Even so, the reappearance brings new details. The first photometric readings indicate that its brightness is lower than before, consistent with cooling and reduced outgassing. The coma, once a bright halo of vaporized ice and dust, now appears smaller and more compact. Yet it's still visible, meaning some level of sublimation is continuing even at this greater distance from the Sun. That residual activity is giving scientists an invaluable chance to study how long solar heat lingers inside a body that has spent most of its existence in deep interstellar cold. Spectrographic follow-up is underway to measure any lingering gas emissions. Early spectra suggest faint traces of carbon monoxide, one of the last volatiles to sublimate at low temperatures. This detection fits perfectly with the predictions made during the observation gap, that deeper layers of the nucleus might still be venting slowly as trapped heat continues to migrate outward. Each emission line adds one more data point to the thermal model, helping researchers estimate how thick the insulating crust has become since perihelion. Trajectory recovery isn't only about position, it's about behavior. By tracking 3I Atlas's movement night after night, astronomers can detect whether its spin, acceleration or jetting patterns have changed since before the gap. So far, the new light curve suggests a slight stabilization. The erratic flickers seen in November have largely smoothed out, implying that the surface jets have weakened or shut down entirely. That makes sense. The farther it moves from the Sun, the less energy there is to drive volatile release. Still, even small deviations are being scrutinized. Analysts comparing orbital data from different observatories have found an almost imperceptible offset, a difference of less than 1 arcsecond between predicted and observed positions. That's an extraordinarily small variation, but it confirms that outgassing effects, while fading, have not vanished completely. The object is still subtly reacting to sunlight, still exerting minute self-thrusts that shape its final trajectory. In many ways, this phase marks a transition, from crisis to calm, from rapid change to steady motion. The object that erupted with gas and dust near the Sun is now cooling and coasting through the inner solar system's outer boundary, heading toward the orbit of Mars. Its behavior is becoming more predictable again. But for scientists, that predictability is just as important as the earlier anomalies. It means that models of interstellar comets are improving, that the physics governing these alien travelers is now measurable, not just theoretical. Beyond the data, there's also a quiet sense of perspective settling in. The trajectory recovery confirms what many suspected. 3I Atlas is leaving us. Every night it drifts a little farther from the Sun, its path carrying it back toward the darkness between the stars. Its speed ensures it will never return. In a few months it will fade beyond reach of even the largest telescopes, becoming another invisible wanderer among billions. For now, though, astronomers continue to log its position, refining the outbound track with each new measurement. These final observations will define its official interstellar trajectory, a line etched into the sky that records exactly how it passed through our neighbourhood. Now that 3I Atlas is visible again and its data stream is resumed, discussion across the global astronomy community is accelerating. Forums, university networks, and research teams are all weighing in on what this interstellar traveller has revealed and what it challenges. Right now, 2 main schools of thought are emerging. The first group, largely composed of comet specialists, views 3I Atlas as a textbook example of natural cometary behaviour. They argue that every anomaly seen, the brightness drop, the misaligned tail, the residual outgassing, can be explained by ordinary physics. To them, 3I Atlas is behaving exactly as an icy body from another system should when it encounters solar radiation for the first time. Volatile layers erupt, dust releases unevenly, the spin changes, then the object stabilizes and continues outward. The second group, however, is looking deeper into the details. They agree that the object is natural, but they see the scale and timing of its reactions as unusual. The rapid chemical changes, the lingering outgassing weeks after perihelion, and the slight non-gravitational thrust all seem more intense than what standard thermal models predict. Their conclusion is that 3I Atlas may possess a more compact or complex internal structure, perhaps multiple compositional layers that respond differently to heat. This idea is fueling new simulations aimed at understanding how interstellar objects form in alien star systems, where the chemistry and temperature profiles differ from our own. Conferences and live panels are now dedicating sessions to this debate. The European Space Agency's Planetary Science Division has already circulated preliminary findings, suggesting that the higher-than-expected carbon monoxide content points to an origin in a very cold region, far beyond the frost line of its parent star. Meanwhile, researchers at the Harvard Smithsonian Center for Astrophysics are comparing 3I Atlas's trajectory and activity patterns with those of 2I Borisov, the only other confirmed interstellar comet. The similarities, particularly the gradual fading and slow rotation changes, reinforce the view that interstellar comets may share common structural properties despite coming from entirely different stellar environments. At the same time, smaller observatories and independent astronomers are contributing vital observations. Many have uploaded raw data and imagery to shared public databases, allowing anyone to test models and reproduce results. The openness of this collaboration is unusual, a reflection of just how significant this discovery feels. For the first time, a global network of professionals and amateurs is collectively watching an object born around another star system as it interacts with ours. While the debate continues, one consensus is already forming. 3i Atlas has redefined expectations of how resilient interstellar material can be. Its survival through perihelion proves that not all foreign visitors are fragile. Some can endure extreme solar heating, shed mass, and still remain intact. That resilience suggests that fragments of other planetary systems might persist long enough to travel between stars regularly, perhaps far more often than previously thought. The discussion is not just scientific but philosophical. In think pieces and interviews, astronomers are reflecting on what it means to witness such an event. 3i Atlas has turned abstract theory into something visible and measurable, a living reminder that the space between stars is not empty, but filled with remnants of other worlds. Some call it a messenger, others a survivor. All agree it is a bridge, a material link between our solar system and the unknown systems beyond. For now, the debate continues in real time. Papers are being drafted, peer reviews requested, and new observations scheduled as long as the object remains visible. The focus will soon shift towards summarizing what has been learned before the comet fades for good, an effort to preserve the story while it's still unfolding. As December progresses, the pace of observation is beginning to slow, but analysis is accelerating. With the data now consolidated and the trajectory confirmed, astronomers are turning their attention from daily monitoring to understanding the bigger picture, what 3i Atlas has truly taught us. The first lesson is one of expectation versus reality. Before perihelion, prediction suggested a routine event, a brightening phase, a solar pass, and a slow fade. Instead, the object revealed how unpredictable interstellar matter can be when exposed to sunlight for the first time in millions of years. Every stage, the unexpected brightness dip, the misaligned tail, the asymmetric outgassing, the subtle trajectory deviation, demonstrated that even small variations in composition can produce major differences in behavior. The second lesson concerns resilience. Many assumed an object of this type would fragment completely during perihelion. It did not. Despite violent heating, rotational stress, and gas loss, 3i Atlas survived. That survival reshapes how scientists view interstellar bodies. They are no longer seen as fragile relics that crumble under pressure, but as robust travelers, capable of enduring stellar encounters and continuing their journeys through the galaxy. A third insight comes from the composition data. Spectral readings confirmed that 3i Atlas contains a mix of water ice, carbon monoxide, and complex organics, nearly identical to the chemistry of long-period comets from our own system. That similarity implies something profound. The building blocks of comets, and possibly of planets, may form under comparable conditions across multiple star systems. It strengthens the idea that the raw ingredients for life's chemistry are not unique to our Sun but widespread in the galaxy. There's also a lesson in humility. Even with today's most advanced instruments and predictive models, scientists couldn't anticipate every twist of this event. The small deviations in motion and brightness were only understood because of round-the-clock global cooperation, hundreds of observatories sharing data, calibrating instruments, and checking results in real time. The encounter reminded researchers that modern astronomy is no longer the work of individual telescopes, but of a planetary network watching the cosmos together. The experience has also shaped how future missions will be planned. If another interstellar visitor is detected, and surveys like Vera Rubin observatories are expected to find many, space agencies now have a clearer roadmap. The 3i Atlas case shows which instruments to use, what to monitor most closely, and how to predict physical reactions as these travelers pass near our Sun. Already, proposals are being drafted for dedicated interception probes that could rendezvous with the next such object before it departs again into interstellar space. Beyond the data and models, there's an emotional dimension that scientists rarely mention but many now acknowledge privately. Observing 3i Atlas wasn't just a technical achievement, it was an encounter with something ancient, a piece of another solar system that wandered into ours by chance. For a brief moment it became part of our sky, revealing how similar and how fragile cosmic matter truly is. Now, as it fades into the distance, the community is quietly reflecting. The interstellar visitor came, changed, and continued onward, leaving behind numbers, spectra, and images that will be studied for decades. It also left a reminder that even the most ordinary speck of dust may carry the history of another world. The final stage of this story is already unfolding. 3i Atlas is receding toward the outer solar system, its activity almost gone, its glow reduced to a faint dot against the stars. But its influence remains in the models it improved, the collaborations it inspired, and the curiosity it reignited about what else might be drifting unseen between the stars. It is now the middle of December 2025. 3i Atlas has fully cleared the inner solar system, moving steadily outward along its hyperbolic trajectory. For astronomers, this is the quiet stage, the long outbound path where activity fades, data slows, and what remains is a final stream of faint light and numbers. Yet this is also where its true nature becomes clearest. The latest tracking data place the object well beyond 1.2 astronomical units from the Sun, heading toward the outer planets at a speed of roughly 42 kilometers per second. At that velocity, 3i Atlas is already escaping the gravitational reach of the Sun, its course carrying it past the orbit of Mars and into the region where solar radiation weakens and interstellar darkness begins to reclaim it. Its light curve continues to dim, now hovering around magnitude 17, visible only to large observatories under clear moonless skies. The coma has contracted almost completely, and the tail has become a faint streak, little more than a trace of dust particles lingering behind. Observers describe the scene as quietly haunting. In deep field exposures, 3i Atlas is no longer the lively reactive body it was in October. It now appears motionless, a small point of reflected sunlight moving against a background of distant stars. But those who have followed it since its arrival see more than a dot. They see the conclusion of a long interstellar journey that began long before our species existed. Right now, research teams are finalizing the last measurements of its outbound motion. These data will define its final orbital solution, the precise mathematical description of its path as it leaves our solar system. When plotted on celestial maps, the line extends outward through the plane of the ecliptic and into the constellation of Centaurus, marking the direction of its escape. It will continue that way indefinitely, unbound and untouched, carrying with it every trace of what it learned here: the dust coating of solar heating, the faint residues of outgassed carbon, and the thin shell of material that once flared under our Sun. As it drifts farther, sunlight diminishes to less than 1/4 of what it felt at Perihelion. The object's surface, once scorching under intense radiation, is now cooling rapidly, falling back to temperatures near -100 degrees Celsius. At those conditions, the last pockets of sublimating gas freeze solid again, sealing the fractures that once vented violently. 3i Atlas is going dormant, returning to the deep space state it knew before it entered our system. Astronomers expect that within weeks, the object will fade beyond the reach of all but the most powerful telescopes. By January, it may disappear completely from optical detection, surviving only in the archives, a long column of positional data, brightness logs, and spectra stretching across weeks of coordinated effort. Its departure marks not an ending, but a beginning for analysis. Every recorded detail from this encounter will now feed into new models of interstellar material, how it travels, how it reacts to stars, and what it tells us about the places it came from. There's a quiet understanding among the scientific teams following it. Objects like this don't belong to any one star system. They are wanderers, the cosmic debris of planetary formation, fragments cast out by gravity into interstellar space. 3i Atlas simply passed close enough for us to see it, to measure it, and to learn from it before it moved on again. As the final tracking sessions wind down, researchers are leaving their last notes in logbooks and shared archives. Most record the same thought: this may be the last time humanity ever sees this object. It will continue outward for millions of years, crossing the cold gulf between stars until it drifts into another system as silently as it entered ours. And yet, its passage will not be forgotten. The story of 3i Atlas, its subtle deviations, its survival, its chemistry, has already joined the record of interstellar exploration. Future generations will read its data as a milestone, the moment we learned not only that visitors from other stars exist, but that we can study them, understand them, and witness their transformation up close. Now, as the object fades beyond the outer limits of our reach, the story closes the way it began, with a sense of wonder. Somewhere beyond the orbit of Mars, 3i Atlas glides through the void, still spinning slowly, its surface dark and silent once more. It carries with it dust from our Sun, just as it carried the memory of another long-forgotten star when it arrived. And as it leaves, it becomes what it always was, a traveller between worlds, continuing its endless journey through the dark, carrying fragments of two solar systems on its surface, one it left long ago and one it will never return to again. Tonight, as the data streams slow and the last exposures come in, 3i Atlas drifts silently away from the light of the sun. It's no longer an event on our screens or a signal through the static of observatories. It's simply a point of fading light, moving outward through the dark. The noise of the instruments fades with it, leaving only the quiet realization that we have just witnessed the passing of something older than everything we know, a fragment of another system, a visitor that crossed through ours for a brief and unrepeatable moment in time. Every orbit, every measurement, every flicker of its brightness tells a simple truth. The universe is connected by motion. Matter drifts, stars shed, systems exchange fragments. Our solar system is not a closed world, but a crossroads, a place where travellers from distant suns occasionally arrive unannounced, stay for a few weeks of human attention, and then disappear again into the black. 3i Atlas was one of them, a quiet reminder that our home exists in an open ocean of cosmic traffic we're only just beginning to chart. For the scientists who tracked it night after night, the object is more than a comet. It's a story in motion. Its light curve is a heartbeat, its changing tail, a gesture, its silence, a lesson in patience. The instruments that once measured its path now rest, but the data remains. Tens of thousands of readings that will be studied long after the object itself is gone from view. Those numbers, cold and precise, hold the memory of its passing more faithfully than any photograph could. As we look up tonight, it's already billions of kilometers away, its path fixed, its destination unknown. It carries dust from our sun now, grains of silicate and carbon that will someday drift across another star's light, perhaps to be seen by another civilization asking the same questions we ask now. There's a quiet poetry in that. One object, two journeys, one beginning, two skies. And somewhere, in the silence beyond the planets, 3i Atlas continues, unseen, untracked, and unbroken, turning slowly through the darkness between stars.